Right, so I think we can get going. Welcome everybody to the 9th webinar in the Human Behavior Change Project webinar series. Today we will have Professor James Thomas telling us about finding and extracting evidence. And before we start hearing about that, could I just ask you, James, to introduce yourself, please?
Hello, yes, thank you. I'm James and I'm based, it's another part of UCL called Epicenter, where we do systematic reviews to inform policy. And we have another stream of work around information technologies, computer science, to make evidence synthesis more efficient.
Exciting stuff. So what we're going to do now is we're going to have a presentation which will last around 25 minutes. And then we'll have a discussion after the presentation. So we're looking forward to your questions. Please make a note of any questions you have as they come up during the presentation, and we will answer them after the presentation. And in addition, if you see questions being posted in the Q&A, you should upvote them if you think they're good questions and you want them answered, and that way the questions which have the most votes will be answered first. So we may not be able to get to all the questions, but we should get through most of them. Usually we get through most of them.
Yeah.
Yes, any questions which we don't get to, in case there's a very lively discussion, will be recorded and stored, and answers will be posted on the Open Science Framework. Recordings will be made available after so the recording of the whole webinar will be posted on the Open Science Framework afterwards. And you as registered participants will get links to watch it again. Great, so let's get on with our presentation. I'm really looking forward to this.
Hello, I'm going to talk about finding and extracting the evidence. So what I'm going to cover this afternoon or this evening or this morning, depending on where you are, is around the information extraction and the information identification within the Human Behavior Change Project. I'm going to talk a little bit about where this sits within the overall project, and then I'm going to talk you through a little introduction to finding and extracting the evidence, and then think about what this has meant in terms of the HBCP. Where have we got to? What are the remaining challenges, and what we're doing next? So in terms of where this information extraction and evidence identification sits within the overall project, it basically sits across the whole project. This is a depiction of the project and its main components. And really one way of thinking about it is that we begin, as many projects do, with unstructured data. We have research reports which have been published in lots of different formats. And one of the things we first of all have to do is say, well, actually, is this information relevant to me at all? So we've used some machine learning to do that. And absolutely critical to this project has been the development and the publication now of the ontologies, which provide structure and definitions to the knowledge which we're using in this system. So absolutely critical there. And then we have information extraction. I've got automated information extraction, but also we've got manual information extraction as part of the project. And critical here is the information extraction is carried out against the ontology. So the ontology provides the structure and the meaning and the relationships between the concepts against which we then assign categories within the research reports and data from the research reports. So that gives us properly structured information about the research. Once we've got that, we can then use the research. So there are two ways of doing that. One is looking and querying the database, looking and querying the ontology, and another is using the prediction system. So those are not focuses of what I'm talking about this afternoon, but they're an important part of the system in order for the system to be available to end users. So I'm going to be talking more about the sort of like the back-end components of the system, the finding of the research and the extraction of information in order to create this database of structured research data on which then the sort of like the user-facing elements of the system can sit. So I'm going to start first of all thinking about finding the evidence. So first of all, what does this involve? Well, first of all, our starting point is that we don't want decisions that affect people's lives to be made on the basis of incomplete, biased subsets of research. Ideally, we want all relevant research, but at least we want an unbiased subset of research. So we want to have that at the foremost of our minds when we're thinking about where we're finding research from. Another important constraint and principle is that obviously we are republishing data here. So we can't take commercial data which has got license restrictions on it. We need data which are open access. So the largest and relatively new source of open access bibliographic data is the OpenAlex dataset, which took over from Microsoft Academic about 18 months or so ago. And we evaluated the coverage of this, and we found that it was completely in line with our needs. It actually had more content in it than the PubMed and Embase, etc., the usual sources that we use for systematic reviews, and it's open access, so that's great. And an important caveat here, of course, is that I'm talking about bibliographic data here. And while bibliographic data may be open access, this is another story for full text reports. Lots and lots of academic papers are closed access, and we can't easily republish them. So that's a challenge for later, which I'll talk about and touch on later. But given that OpenAlex is our main source of data, and given that it contains 250 million records, and there are more arriving all the time, which is great, we want to keep up to date with emerging research, the question then becomes, well, how on earth do we find the relevant research that we're interested in? And we've used machine learning for this, and we've got a pipeline in place that we've mentioned in a couple of the other webinars. So I'll just refresh your memories on this one. So the aim here is to maintain a surveillance of the literature. Many organizations such as NICE maintain evidence surveillance to keep on top of the literature as it emerges. What we want to do is keep on top of the evidence base as it grows. So we've got OpenAlex. We're starting to look at clinical trials repositories as well, because we know that that's not a source of bibliographic information that goes into OpenAlex at the moment. New papers arrive every couple of weeks. Actually, recently we're now actually able to query the OpenAlex database every hour, I think, if we want, which would supply us with an awful lot of information very regularly. So we'll have to see exactly how frequently we need to update the system. Usually we're going every 2 weeks, every month or so. And then within the system, which has been integrated within the EpiReviewer system, so anybody using that is able to use it, we have reviews. We have databases, we have systematic maps, we've got the databases that we use for the Human Behavior Change Project. And within these, what we do is we sort of subscribe. We say we want this review to be kept up to date with new research as it emerges. And what we do then is for each review which we want to keep up to date, we create a machine learning model, a distance model. And every single new paper comes through the system, is compared with that model. New papers that look as though they're relevant to our HBCP domains in this case are automatically added to the relevant reviews. And we also use other machine learning processes to filter them down. So for example, the Human Behavior Change Project is focused on RCTs, so we use an RCT classifier to make sure that what we're putting into the database are randomized trials and not other types of study design. And what that enables us to do is to stay on top of the evidence base as it's emerging, supporting living evidence surveillance and living reviews, living maps, and also making sure that we're up to date. Last webinar that I presented in, we looked at some of the user-facing tools. I'm not going to look at these in detail today. You can refer to that webinar if you're interested, but the Human Behavior Change project has got 2 databases, and it's a way of visualizing and querying and downloading the results. So just to finish on the identification of evidence, there's one other workflow that I was going to mention to you, which is using the system but isn't using all of the system. It's the COVID-19 research surveillance that we've been doing. It doesn't use the ontology because it's COVID-19 research, so it's not just behavior change, doesn't make predictions, and has its own information extraction, which is about COVID-19. Many of you may well have seen it. It's been maintained throughout the pandemic, and it's now fully automated. So we've got, I don't know how many hundreds of thousands of records we've got in the system now, but it's an awful lot. And the records are categorized and put into these different categories, as you can see on this bar chart here. So the map workflow I thought was particularly interesting to highlight for this presentation, because we've got a workflow here which is about finding the evidence, the OpenAlex as the source, is it about COVID-19, and then which category does it belong to? And so we've got a finding the evidence component, and we've got an information extraction part component, which uses a similar model to some of the human behavior change models, which is a BERT-based model. And so we're moving here from finding the evidence through towards thinking about extracting information about the research. So we're going to move now on to a consideration of information extraction within the project. So what is extracting information? What does that involve? Well, if you've ever carried out a systematic review, it's very similar to what you've done there. You have a research report and you capture and you record data about that research project. We capture categorical data. So like I had on that previous slide there, what type of, what parts of the COVID-19 map does it belong to, or what behavior change technique does something utilize? We have textual information, so free text about the characteristics of an intervention, for example. And we have numeric data, effect size estimates, how many people were in a particular category. And we have two objectives really to this information extraction. We're interested in training machine learning models to undertake the task automatically. And also within that, we're actually interested in using the data to evaluate the models. And we're also interested in generating a consistently classified data set, which we can use for further research, and already are, and prediction. So what information is extracted? As I said, those of you who've conducted systematic reviews will be very familiar with this. We obviously want to capture information about the population of the study, its setting, the behaviors, the outcomes that we're interested in here, and effect estimates. And there we're capturing numeric information, effect estimates. And you can see some of the other characteristics and domains of information that we're extracting here. Particularly important in the context of this project is the categorical information about BCTs, behavior change techniques. And if I go on to the next slide, as I mentioned before, this information extraction is done by people and it's done automatically by computers. So an example of the user interface when we've got people doing the information extraction, this is the EPI reviewer interface. We've got some of the categories here, which are embedded in the structure of the ontology on the left-hand side here. And we can see I've circled here, website, computer program. And as is typical when you're doing data extraction in a systematic review, information extraction and annotation in this case, we've got a PDF file on the right-hand side here, and we've highlighted here the text website to associate it with that. And that helps when you're doing a review. It helps to link the data in the PDF or the Word document or whatever you're extracting from with your categorical and numeric data that you've extracted. So you've got an instant link between the two to justify why you've selected a particular category. And also what we've got in the text box here is the person who did this particular piece of information extraction also extracted the context around this. And this was particularly important for building machine learning models in the context of this project. So we've got this precise category here, the fact it's website linked to the category here, and we've also got the context around that, which is helpful for machine learning. Looking in a little bit more detail at the results, we can see here the types of data that are extracted. So we're interested in characteristics of the population, the age, gender, ethnicity, etc. And you can see the types of annotations, the types of text which are identified along those particular categories. Again, here we've got the outcome value, the effect estimate, and the content, etc. of the BCTs. And the accuracy statistics. Information extraction is hard. You can see here some of the best scores were just over 50, 56 on F1, but this is a difficult task. And also if you think that what we're wanting to do is to line up lots of correct extracted information in order to get a true representation of the study, you can say that this is a tricky process. So while some categories had lots of data on which to learn, others had very little. So this is a challenge not just because there wasn't much in the annotated data set, but actually for some types of interventions, there may only be 2 trials in the world about something. And that's simply not sufficient information really to be training a machine learning system to recognize particular intervention characteristics. We might just have everything available. We can't even train and then test how good we are. We just don't have enough data. It's also, and that paper that I meant that I took some of those screenshots from reports this, it's very difficult to extract the structure of a trial, how many arms it has from a published report. So what we're doing now to address that is doing some image recognition and image manipulation work on the consort flow diagrams that we find in reports of randomized trials. So many of you who will have seen these, and I presented on this at the last webinar that I presented in, so I'm not going to go into too much detail, but I'm just going to highlight here because it's relevant for information extraction. We've got the flow diagram here, and then what we do is we use image recognition to identify the boxes in the flow diagram. We then identify the coordinates of each of the boxes. We extract the text within each box separately. And then we use optical character recognition to recreate the text. So we've got a lot of data there in terms of where the boxes are on the page and what the boxes say. And what we end up with are structured data. And you can see here what we've got is that's that same flow diagram. We've got the text from the various boxes, assessed for eligibility, etc. And we've got the coordinates of the boxes, and we can calculate other metrics such as how far they are from the top or the bottom and from the center and that kind of thing. So using that data, what we're able then to do is to create a structured machine readable representation of the study. What's really important here is instantly we then know how many arms a given study has, how many people were in the study often, because this is reported. That's the point, part of the point of this flow diagram. And often, though not consistently, the labels that were assigned to the arms, the intervention and control comparison group. So really useful information with which we can then structure other information extraction about the study. Last of all, no presentation at the moment on this would be complete without some mention of ChatGPT. So there's likely potential here to help with information extraction and study identification. So for example, I ran some simulation studies based on data from a review we published last year on debunking vaccine-related information. So there were studies which were included and studies which were excluded. We had about 1,100 studies in total, 44 of which were included, the rest were excluded. And I've got the results here from GPT-3, which was the first GPT model that people got really excited about, then ChatGPT, and then GPT-4. And what's interesting here is we can see improvements, especially in the precision statistics here, as we go through the generation of models. And also the fact that as I change the prompts, change the way in which I ask the questions of the model, I get slightly different results. So there's some encouraging and potentially useful results here, but we still have to be cautious. And I will just show you an example that I've got here of why we need to be cautious. Okay, so here is GPT-4, and I asked GPT-4, can you list behavior change techniques described in the behavior change taxonomy by Suzuki? That was my prompt. And the robot smiles and presents me with this list: goals and planning, feedback and monitoring, BCT V1. This all looks good. This looks good. Scrolling down here, this just looks just like we're used to. We've got the 16 categories, looks great. And then it says these BCTs provide standardized language for describing and reporting interventions in behavior change research. Great. Well, it looks as though GPT-4 knows the behavior change technique taxonomy. That's very nice to know. So then I've said to GPT-4 here, what behavior change techniques are present in the intervention described in the following text? So I've got some text here, which is about It's one of the smoking cessation studies in the review in the Human Behavior Change Project, and it's talking a little bit about prizes and rewards and that kind of thing. So it tells me the intervention described has several behavior change techniques. It says from goals and planning, it's got 1.4, action planning, it's got feedback on behavior, it tells me why, prompts and cues, rewards, future rewards, reward approximation, etc. So I'm not going to go into the detail of whether or not it got every one of those categories right, but what you can see from this is actually it's a step change above what we're able to do with previous models. And it is what's particularly interesting is that I haven't trained this model at all. This has simply come from the pre-trained language model, which has then been deployed online. So if it really does know about the BCTs, and if it can then just tell me and classify text according to which BCT are in it, that's potentially very, very useful indeed. However, if we go to my other screen share, where is that? Document 1, here we go. If we look in a little bit more detail, I've just copied and pasted this out, and this is work that Ella sent me earlier today. What we can see is actually there are places where classifications and terms in the taxonomy either are in the wrong place, so this should be 10.4 rather than 6.4, or they're completely made up BCTs in here. It seems to do very well at the top of the list here, and as we get further down, it gets a little bit more hazy. So we've got made up BCTs, etc. And actually, once you look at the thing as a whole, let's just go back to my original slides now. The ChatGPT in this case made up 10 BCTs, missed 18 of them, and did not correctly group 18 of them. So what we don't know, of course, is whether that would affect its classification. Maybe that's simply an artifact of the way that it was responding to my prompt and listing them all out. We just don't know. But one of the things which is relatively clear now is that we can't rely on them as being repositories of information which they can then regurgitate accurately. The other limitation that I think is worth us bearing in mind is they don't usually contain closed access papers because they're closed access by definition. And therefore we're seeing all of these question answering systems pop up left, right, and center. But we really must be thinking about that point I made right at the beginning about not wanting decisions to be based on a biased or a misleading subsample of the research. At the moment, these systems are not actually engineered by design to give you correct answers in that way. So that's a little bit on ChatGPT, a slight aside, but wouldn't have been complete without it. So it does feel, in conclusion, as though study identification is making really good progress, getting close to being solved, though not totally solved yet. Information extraction is challenging, and a large language model may offer a step change here, but we're going to have to do a fair bit more research yet.
Wow, really exciting stuff, James. I wonder if I can start or get the discussion going with the first question myself.
Sure.
So, assuming that something like a large language model is being used for information extraction, how do you, because it kind of gives you back text, right? So how do you sort of put that into a pipeline where you're sticking the extracted information into another tool, which is not taking text, but IDs or something like that? This seemed like a missing bit in the whole.
Sorry, talking of missing bits, I missed a little bit of your question there.
Ah.
It might be because the Wi-Fi's got busy with people
So
coming
I'll
in.
repeat. So I thought this demo of ChatGPT extracting BCTs was really exciting, but I get that it's not ready to be used in that way because it's not sort of having the information. But another question that occurred to me was, it takes text and it gives out text. Now, I was wondering sort of what would you need to do to get from the text that it gives you back with the BCTs and so on, sort of put that in a database afterwards?
Yeah, I mean, that's one of the challenges. And what I have been doing when I've been doing some of the other bits of research is it gives you back text, but you can tell it to give you back JSON formatted text. So what I've been getting it to do is saying, I'd like you to return me your results in this format, in a JSON format, and this is the structure I want you to do. And ChatGPT 3.5, the original ChatGPT that we first played with, was quite good at it. GPT-4 is very good at it. It doesn't create me horrible malformed JSON anymore. It just actually does return JSON.
That's really interesting. So it sort of knows how to encode. So JSON, for those who in the audience who maybe don't know, is a kind of structured data format, right? Where you have some structure that you can then use computationally. And so the language model itself can format the data that way.
Yeah, and for other purposes, if I wanted a RIS version of some references, so the type of reference that you can then import into EndNote or something, I've copied and pasted that into GPT-4 and said, give me a RIS version of this, and it knows what RIS is and it gives me the format, and it looks like RIS, but this is another of the little quirks about the system. It didn't really spot the fact that actually there are 2 spaces after the tag, not just one in the specification. So I still had to do a find and replace and sort it out. And then I had a nice little chat with it and said, didn't you know that there were 2 spaces after the tag? And it said, oh yes, I did know that, but it didn't actually translate into it actually applying the 2 spaces.
Really interesting. So I think we can start answering or discussing the questions which the audience have asked us. So our top question at the moment is by an anonymous attendee who asks, are papers being tagged with metadata as they're uploaded to OpenAlex to help with information extraction? So
yeah, that's a great question, and it's something that there are quite a few people who are asking, and there's been questions asked over the OpenAlex team. I mean, if you're interested in that kind of thing, there's a Google group for OpenAlex where you can talk directly, and the team developing it chats backwards and forwards, and other people using it supplying information. So it's a really useful group to get into. So yeah, I mean, one of the things that we do wonder is whether either within the actual OpenAlex repository or, in this wonderful world of linked data, we could quite happily put up a set of classifications against OpenAlex records, which somebody using OpenAlex can then link to, because we can use the same identifiers, and so they can be seamless. So the question is a really good one, because I do think that we should be thinking about an open, accessible, and increasingly sophisticated and rich set of metadata around research records. But that doesn't necessarily mean they have to actually be an OpenAlex. I mean, OpenAlex Excels is semi-leading the way on it, in that the classifications, the topics that it puts against records are all identifiers from within Wikidata and have Wikipedia pages against them. So you can start with an OpenAlex record, and you can go through, and if you look at the Wikidata record, then you get lots and lots of identifiers with your UMLS, the Library of Congress, MESH. There's lots and lots of places where those identifiers then link to. And so I on one level you think, well, it would be nice if it was just all in one place and within OpenAlex itself, but it might get a bit much for the teams to sort of manage lots and lots of different contributions. But actually, so long as we're obeying reasonably easy to follow rules about linked data, then it's nothing stopping us putting up our own repository of metadata which links through to OpenAlex.
Really interesting. There was a sub question which doesn't seem directly related, but I will pick that up now, because otherwise I think it will disappear because we discussed the OpenAlex question. So this is by Dr. Jean Davis, who asks, systems such as Turnitin are better testing identifying this type of AI in student papers. So I think here the question is about ChatGPT generating text and about that sort of impact on education. So I don't know if you have some comment about that, James. What do you think? Is everybody asking you to be an expert on this at the moment in your department?
Yeah, I mean, there is a working path group, which I'm not part of, as you see, which is looking at this. To be honest, I hope Jean doesn't work for Turnitin, but I think that it's kind of like going to be a losing battle. I really can't see how you can detect the use of these systems beyond the fact that sometimes, you know, this is the word hallucination seems to be a very popular at the moment. They make up citations and things, are, you know, that kind of thing you can spot. And at the moment, it's relatively easy to spot because students haven't really quite grasped the sort of like the limitations. And so they're here and there, you can say, well, actually, that just, you know, that none of those citations exist. You clearly just either made them all up yourself, which, you know, which is not outside the bounds of possibility for those who've done student marking, or it's come from ChatGPT. So there's that, but basically I can't see how, you know, it writes reasonably good English. It's, you know, some of its turns of phrases are spottable, but if someone uses that to create a first draft and then goes through and edits it a bit, I think that's going to be part of the process, and it's going to be part of the process for a lot of writing. So I think we have to live with it and find other ways of, you know, thinking about student assignments and what it means to mark them.
It's a really interesting development for educational purposes. So I heard some study found that the automated checking for ChatGPT text or for language model generated text was biased in the sense that it gave more often false positives for non-native English writers, which I thought was, so this has, I think it has to do with how surprising the text is. So if it's your first language, you're sort of maybe have more alternative ways of formulating things. And then in a second language, you have maybe a reduced, but anyway, this was just one study, but I was really interested. But I totally agree with you, James, that this is something which will change educational assessment, basically. And yeah, I'm all in favor of oral discussions too, but maybe we should come back to our questions. So thanks for these really interesting questions. Our next question is, can this system be used in a non-controlled trial repository, e.g. qualitative research and non-experimental research? What do you think, James?
Yes. Got a longer answer than that. Yes, a lot of the ways in which the system works is agnostic in terms of the type of research that's being done. So all of the system that I showed you today, apart from one part of it, would work in theory with qualitative research, certainly non-experimental research. One of the elements of the system that I mentioned was that we were looking for randomized trials for this part of the project, in which case we're putting the papers through a randomized control trials classifier. So that part of the system is not a great fit for qualitative research, but the rest of it is fine. I think the only other thing that's worth bearing in mind is that at the moment, these systems really do like precise jargon. You know, if you're dealing with proteins, you're dealing with drugs as well, which have really quite precise names and quite unique names, then the systems work better than if you're dealing with concepts which have multiple meanings in different contexts. So, you know, some qualitative research might be looking at people's understandings and the meanings that they take from a particular phenomenon, and there you may well be using vocabulary which is used for completely different purposes in another context. And so there, you know, it's harder for these systems to work well. But having said that, you know, the scale and the speed of these things are changing. I don't want to be too confident about even saying that now, because I think it's partly that just the scale of the models now is enabling us to be much more precise about the context within which language is being used. And Jana, you know more than this about this than I do. But I think I would be much less confident now saying even that you just assume that in qualitative research things are going to be a bit fuzzier and you wouldn't get quite such good performance.
Yeah, I think it's an empirical question, one which we haven't sort of tried to address, but at least in theory, there could be such a thing as a qualitative research detector, right? Like you have a randomized controlled trial detector. Sure. There could easily be a model or a trained system which looks for qualitative research in a certain domain and then tries to do something like a qualitative synthesis on that, right? We haven't built it, but maybe there's somebody in the audience who wants to give that a go, and then we would be super interested in seeing how that works and what the challenge areas were, right? I think you mentioned, James, I think you mentioned that one of the challenge areas for the trials for the information extraction was really getting the structure of the trial right. Yeah. What was being compared with what? And how it all sort of fitted together. And this aspect is still challenging, isn't it?
It is still challenging. I mean, on qualitative research, the other challenge there is putting boundaries around what is qualitative research and what it isn't. But you know, that's another challenge. Because I mean, you get lots of people in a room, you'll get different definitions and different boundaries. Whereas an RCT is easier. Though I mean, there are little elements of you know, controversy, but not to the same degree. On the structure of a trial, I think that's been a big challenge, which is why we've gone down the consort flow diagram route, because that actually is a structured picture and it shows us how many arms and etc. what's going on in the trial. Because if you can imagine, you've got a sort of several paragraphs of texts that talk about the interventions. And it's hard enough just to take text like that and assign which particular behavior change techniques are being used at particular elements there, let alone say that these are the ones which have been assigned to arm A, these are arm B, these are arm C, or whatever in the trial. So that's why we're thinking that the consort flow diagram approach will at least tell us how many arms there are, and hopefully arm labels, which is another challenge because they're not used consistently throughout a paper. People like to, vary the language they use to describe things for, so it's not too dull to read. Just dullness is not a virtue when you're thinking in terms of a machine reading it. So, or rather, dullness is a virtue. The avoidance of dull isn't. So that challenge aside, at least we'll know how many arms we're looking for, and then that will help us, I think, in terms of trying to say which BCTs belong to which arm and which population characteristics there are. I mean, the other thing on that, of course, is the information extraction from tables, which I didn't talk about, but that's the next thing that we're working on. And what's nice about the environment now that we're working in, we can see progress. It's not always as quick as we want, but at the beginning of the project, getting information in structured format of tables from PDFs was just about impossible. Whereas now there are quite a lot of tools which will give you actually a proper tabular structure of the data. So then the next challenge is sort of teaching a machine to be able to read it.
So that's, I see that things like tables are challenging, and I guess extracting information from figures is impossible. So sometimes outcome values are only reported in figures or something like this, and then it's just lost, right? It's just lost information.
It's tricky. It's not totally impossible. Sometimes it's useful to sort of do sort of computer assisted, where you can sort of have someone involved a little bit in that, but it also depends what type of figure it is. I mean, we're really getting into the weeds here, but there are different types of layering in a graphic, and one type of layering you can actually do something with, and another types are more difficult. Peter Murray Rust has done some work on this.
Yes.
In his repositories, you'll find various sort of little pieces of work around extracting numeric data out of graphs in a PDF.
Really interesting. Our next question is from another anonymous attendee who asks, what does extracting information like this help us with? And before you answer that question, I want to just ask one sort of side question, which I think is related, which is why PDFs? So if you can see how these two questions fit together, that will be
Yeah.
super.
Oh, why PDFs? Oh dear. Well, we'd have to go back in history to look at the history of publishing. Yeah, lots of people ask why on earth? How did we end up here? PDFs are basically a nice way of storing a publication ready file. So it
Right,
tells the printer what to print
right,
precisely. That's what it's for.
right.
It's not designed beyond someone printing it out and someone reading it.
Yeah,
And so it's not designed for data extraction of any type or for data reuse. It's simply a good way of visualizing something which will be then printed on a printer. So why it's become the de facto standard for documents online, as a matter for history, but if we knew where we would be ending up, we wouldn't have started from where we did. I don't think. PDFs are universally disliked in the
right.
information extraction worlds because they're so clunky. So if you can imagine a picture of a table on a PDF, we can see that instantly as a table. It's got lines around boxes and everything. Not so if you actually look at how that's represented in the PDF. Pieces of information are jumbled all over the place. It's not linear. It's not actually stored as the PDF format in the way that you see it on the page at all. The lines don't even look like lines. There's all sorts of things and compromises going on. It's a really, really complicated and ugly file format.
Wow.
So you can't just look in the file and get the table out. That is simply a visual representation of the thing. So weirdly enough, what actually some of the computer systems are now doing is they are essentially taking like a picture of the page, they're visualizing it, and they've been using machine learning to say, okay, so this looks a bit like a table. And so that is, so literally that's how it's done with OCR. This looks like a table zoomed out. And so we're going to find those coordinates and then zoom back in again, extract that information, and then try and piece the table back together again.
Sort of like what you're doing with the consort diagrams.
It is, isn't it? It's ridiculous, really, because that information was structured. It was, might have been an Excel file or something at one point, and then we mangled it. And then we've got to reconstruct it again.
Wow. So coming back to the question that we started with, why is this structured information that we're trying to get out of the PDFs? Why is that the goal? What do we need that for? Why do we want to extract information?
Well, I mean, that comes back to the very heart of the point of the project. So, that initial picture I had with all of the unstructured papers on the left-hand side there, and probably the COVID-19 is the extreme example of that. So we've got 200,000 little papers on the left-hand side there. And so, say you want to know, one of the reviews we did was on aerosol generating procedures. Which procedures beyond the obvious ones generate aerosols, which might then increase the likelihood that you'll contract COVID. So you need higher PPE when you're doing those procedures. 200,000 records need to know, in terms of a guideline, which procedures you should be a bit more careful with in a hospital.
Right.
You can't get, so you need to be able to say, okay, so these are the papers we're interested in, but then you've got to say, well, these are the procedures we're interested in. And then you've got to say, well, okay, so, here's the sort of like the risk profile of each of these. And then potentially then you're into behavior change around how you support people to use appropriate PPE and that kind of thing. So there's lots of very detailed information that you need to know about the research in order to use it, which is just hidden away, and we need to take all of that unstructured information and structure it in order to answer a question like that. But you can add ontologies on top of that. I was leaving them to you.
So the thing about ontologies and vocabularies and so on is they sort of provide a careful, thought out structure, as opposed to the accidental structure that you get if you just look at what was published and what was written in the text, because people will write things in lots of different ways and you won't know what that really means unless you're very familiar with or read the whole paper, right? And 200,000 papers, you're just not going to be able to read the whole paper. So the ontology gives you this index and way of organizing things, which has at least some additional organizing structure in it. And then if you use that, if you can match that up accurately to the papers, then you have a kind of powerful way to get to the right thing. Yeah.
And you have a structure which future research could then use. So rather than restarting the process every single time, we can say, okay, so we know that this is the way in which we're describing this type of intervention, this type of behavior change technique. And so we'll use the same vocabulary, we use the same ontology, and then it just fits into place rather than being unstructured and needing structure.
Yeah, really interesting. Thanks, James. So moving on to the next question. The question is, can you share a bit more about how information is extracted automatically by the computer? So I think probably you glossed a little bit over the details of this for probably largely good reason, but
largely good
just
reasons.
a few hints maybe towards these details, like what's actually happening when a computer is doing an information extraction task.
Okay, so let's take age as an example to start with, because that's one that's has got multiple dimensions to it. So age might be represented, it might be in the abstract of a paper, it might be sort of buried elsewhere in the paper, but let's just say we've got a piece of text which talks about the basic context of the intervention and participants, and says the mean age of participants was ... 37. So but then it also says, and there were 480 participants, and 43% of them had a previous quit attempt, for example. So what we've got there is a chunk of text with information about the context, participants, and also buried in there is the information that we are wanting in this case, which is the mean age of the participants. What we might do first of all is to have something which is not very difficult to write, which identifies the numbers in a piece of text.
Yeah.
So we would say, okay, so give me the all of the numbers in the piece of text, which in our case we have 37, did we? And then we had a 40 number as well, and so we would just pull out numbers, and without any context around them, they're just numbers. We don't know what they mean.
So there were sort of 3 different numbers in your sentence, which all describe different aspects of the participants.
Exactly.
And which one is exactly the one you want is a little bit tricky, right?
Yeah. So then what you do is you pull out the text around each number, and you look to see whether that contains clues about the age of the participants. And there are different ways then of doing that for a computer. What you can sometimes do is say, for something like age, it might be reasonably easy because the word age probably appears near that number. That's a very easy use case. Sometimes it won't, but so if you can predict with reasonable confidence that actually we know what the words are, we can set what's called rules up to say, okay, so pull out the numbers, and the numbers which are accompanied with the word age, with 1 or 2 words away from that, we're going to take that as the age, and the job's done. For something more difficult, what we might do is that annotation process that I showed on the screen, where we extract the information and we select the text around that piece of information, and we do that off, in our case, 500 studies in one area, and quite a lot, several hundred, was it, in physical activity as well. And then we have lots of examples of text which we know describes the age of the participants. And what we can then do is we can make a machine learning model there, which says, okay, so here is all the text that describes the age of the participants. And we can then compare that with all the text which describes other characteristics. And we can build a model which then will predict, given a new piece of text with a number, how likely it is that it's describing the age rather than something else.
That's right, because these types of machine learning models, they work on kind of similarities, don't they? Similarities in word meaning, similarities in the context or the structure of the sentence, and so on.
Yeah, and you either get a model which works relatively simply, and doesn't look at synonyms and that kind of things, but just simply assumes that we've got all of the different combinations of words which are likely to appear around age, and essentially, in a little bit like, you can use a logistic regression model for it, and we'll just say, well, the probability of these words appearing near age is this, and when you put some new information or put a new piece of text in, it will then tell you based on that little model. More complicated models then will not just look at the words that you've got there, but they will use a language model or similar, and will then identify all of the words which appear around those words as well. So potentially are more powerful, but potentially they can add some more noise in, but also they're bigger, they take more work. And so one of the things that I think it's important to bear in mind when doing this research is that going for the most expensive and complicated model is not necessarily the best thing for a live deployed system. Actually, a little rule that says any number next to age, if that's good enough for our purposes, is much cheaper to deploy and much simpler to maintain than something which uses a large language model for something like that.
And there's energy costs to consider as well, right? There's environmental costs of computation that have to be somewhere in everybody's minds at the moment. I want to get to a few more questions. So there's one by Michelle S. who asks, what has been the hardest thing about developing a system to extract data in this way? And this was followed up by Tom W. asking, and how as researchers can we help make it easier? I think this is a really interesting.
That's really good questions. Yeah. I mean, there's different aspects of this. So on the last thing that we were talking about, the consort flow diagrams part, the hardest thing about that, other than the fact that we have to do it in the first place, let's not go there, is the fact that there is a template available, but lots of people haven't used it. And obviously for older papers, the template wasn't available anyway. But for this sort of thing, if on the Equator website or on Consorts, there is a template for it, it makes it so much easier if you follow the template, because the system that we're designing, most of the diagrams follow it, so we can build it to suit them. But then when people start adding extra boxes and lines going off left, right, and center, and all sorts of things happening, it makes it much harder then for us to design a system that can read those diagrams. So number one would, in terms of making it easier, just follow the template if there is one for that kind of thing. The other thing would be consistently label the arms in the diagram and in the paper. So if we can get a nice structured diagram out, get the arm labels, and they're the same arm labels that appear in the text of the paper and the tables of the paper, then this task would be so much easier. What makes it really hard is the variability in language that's used.
Yeah, people are so creative in the way they describe things in their papers. But don't you think it would be best of all if the structured data we need was somehow available with the paper, not in a PDF, but in an actual structured format from the beginning? I mean, couldn't we
that
imagine
would be even
that
better?
as being...
Yeah, of course, yes. Well, I mean, there we get on to the fact that in here we've now got an ontology, we've got a way of describing the studies in really, really rich detail. If that was published along with the paper, then it would make the studies much more discoverable, and it would make reusing the data in the studies so much easier. I think that we're getting into sort of like a new sort of vision for how we would go about doing research, but
about reporting research, right?
Well, it's reporting, but it's also conducting it, because there are loads and loads of situations where people who do a research study in almost complete ignorance about what other people have done, partly because it's just so hard to find out what other people have done. It's only later that someone says, oh, that's that's just a copy of what X, Y, and Z have done. Whereas if it was more discoverable and structured in the first place, then we would know that. And so in our area where we're thinking in the smoking cessation and trials, really what we should be doing is looking at the existing trials in an area, and we should be saying, oh, say we need another trial on this, and we should power it in relation to what we already know, so that we're not getting to the end of the study and so if only we powered it a little bit more, it would have given us a clearer answer. So we literally think about our study not just as a standalone study, but how it contributes to the growing body of research in an area. So we start the research with a meta-analysis or with some kind of evidence synthesis, and then at the end of it we can say, okay, so here's the study all reported in the same way in which it was in the previous study, which justified our doing this, and this is how the body of how the body of knowledge now has increased thanks to the research we've done.
Yeah, this is a really exciting vision. I think we have time only for one last question. So according to the ranking we have, can the system judge the study quality or risk of bias? Would it filter out studies that didn't include a consort flow diagram, for example? Yeah. If you answer very quickly, then we could also answer the question, does the system only pick up English language papers? And if not, are there issues with translating concepts?
Okay. All right, I'll answer it very quickly. Risk of bias. What we've used in the existing project, we've actually used the Robot Reviewer risk of bias tool rather than developing a new one. Though there's a new version of risk of bias, the risk of bias 2 is out now, which that doesn't currently do. So we would need to think about that. I think in terms of study quality and risk of bias, rather than thinking about looking at a study and saying that's its risk of bias, it's more that there are characteristics of a study which sort of raise or lower the potential of risks of bias. And so what I'd be quite interested in doing is, rather than thinking about a risk of bias tool, is a tool which which actually looks at assessment and blinding and that kind of thing, and just tells you what it is, and then for different purposes and in different use cases, you can then decide which characteristics and where you want to draw the threshold for it. Well, what's actually important is being able to understand the characteristics of the study, including bias, but not just bias. Would we filter out studies that don't include consort flow diagram? Not at the beginning of it, no, not at the study identification bit. After that, you've then got the PDF identification, the PDF use, where we lose a lot of research because we can't get the closed access papers. So actually that's probably a bigger filter than whether or not there's a flow diagram. And especially with new papers now, thanks to consorts, it's very consistent now.
And English language? No.
It actually is, especially OpenRx is better actually for non-English language research. It's depending on the type of machine learning you're doing. Some models are built expecting only English language. The model that we've got there actually isn't. And we use other characteristics for the citation network, for example, as well, as part of the way in which we find the studies. So we're not just relying on the text and the language to see if something's relevant.
Great, thank you so much, James. This was a really, really interesting discussion. I've learned a lot, and very happy to now close up. Unfortunately, we're out of time. If you have any further questions or comments, please scan the code that's showing on your screen at the moment, and that will take you to somewhere where you can do something with your questions and comments. Our next webinar next week will be on predicting the outcomes of behavior change interventions, and that will be me having a discussion with Professor Robert West, who is one of the key people in the project at UCL in the Center for Behavior Change. And finally, really excitingly, save the date for the 6th of June, where we're going to be launching all the tools and associated resources for our knowledge system. Here are some links where you can access more information, recordings, etc., etc., etc. And thank you very much for being here and listening, and for the great questions.